Okay, so now I'm going to show you an example of computing a 4 by 4 determinant, where again, we'll use row operations to simplify the task a little bit. But I think this example will be all the more illuminating as to how helpful row operations really are. Because computing the determinant of a 4 by 4 matrix with no zeros anywhere is definitely going to involve computing 4 3 by 3 determinants. And that's going to be a fair amount of work. But let's see if there's some row operations we can do. Well, I'll start in the usual way. I'll write determinant of A, because that's what we're going to compute. And that is, I'll just write it in vertical line notation. And so what's that going to look like? So I'll just write out the entries. 3, -1, 4, -5, 6, -2, 5, 2, and then 5, 8, 1, 4, -9, 3, -12, 15. Okay, so the first thing, like we could just start doing Gauss-Jordan elimination at this point, and how would we accomplish that? Maybe divide row 1 by 3 or multiply row 1 by 1/3. That would put a 1 here. But all these other three numbers here that are not divisible by 3, that means we're going to have fractions, and it looks like it's going to get a bit ugly. But I do want to draw your attention to the fact that, look, there's something about the fourth row and the first row. They share some common feature, and that is they're proportional to each other in the sense that what would happen if I add row 1 to row 4 3 times? So in other words, I mean the following. So because I'm presenting my work this way horizontally, I'm going to write the row operation above the matrix rather than beside it to the right. So let's take row 4 and replace it with row 4 plus 3 row 1. And watch what happens. Well, the first 3 rows won't change, so I'll just copy them first. That's the first row, then our second row, third row, and then what'll happen to the fourth row? Well, -9 plus 3 times 3, that's -9 plus 9, which is 0. 3 plus 3 times -1, that's 3 minus 3. -12 plus 3 times 4 is -12 plus 12, which is 0. And then lastly, 15 plus 3 times -5, that's going to be 15 minus 15, which is 0. So hey, that introduces a row of zeros right here. So, well, as we've seen before, if you have a matrix that has a row of zeros or a column of zeros, you can immediately conclude that the determinant is 0. And notice that this determinant really is equal to this determinant. Why am I allowed to do that? Because remember, this particular row operation, adding a multiple of one row to another, doesn't change the determinant. But if we had interchanged rows, or if we had multiplied any of these rows by a non-zero constant, we would have had to make adjustments. We would have had to put an extra scalar in front here to adjust for that fact, whether it be a -1 or a 2 or a half or whatever the case would be. It would depend on the row operation. But the fact that we just added a multiple of one row to another, and the fact that operations of that type have no effect on determinants, is why I was allowed to say that this determinant is equal to this determinant, because certainly they're not the same matrix, right? So they're not equal as matrices, but the two determinants are equal. But since we have a row of zeros, the resulting determinant is going to be 0. So hey, that was great. That didn't take too much work at all. We didn't have to do cofactor expansion. So here's an example of a case where finding determinants can be really easy in a very certain circumstance. What was it that made this easy? Well, this was just a particular case of a more general phenomenon, and this theorem states the general phenomenon. If you have a square matrix that has two proportional rows, really, like think row 1 and row 4 in this example, then the determinant is going to be 0. And this is why, because you can subtract or add one multiple of one row to another to introduce a row of zeros. So that's why if you have two proportional rows, well, then the determinant is going to be 0. But this theorem says a bit more. It says that if A is a square matrix with two proportional rows or columns, then the determinant of A is 0. So it also works if you have two proportional columns. So why is that? Well, remember that transposes do not change determinants. So if you have two proportional columns, the transpose of that matrix will have two proportional rows. So its transpose will have a 0 determinant. But since transposing doesn't affect determinants, that means the original matrix is also going to have 0 as its determinant. So that's why. But the important part is to remember that fact. If you have a square matrix that has 2 proportional rows or columns, it's going to have 0 for a determinant. So that's another opportunity to save some time. And speaking of that, there's another thing we can now shift our point of view towards columns now for the following reason. So the next little blurb here is going to be about column operations. So we've never talked about column operations yet, and you certainly cannot perform column operations on an augmented matrix and expect that to lead you to any sensible result. So I just want to say this once and for all right before we get any further into column operations. We're talking about a very narrow situation right here where we're talking about computing determinants. But if you started to now perform column operations on an augmented matrix when you're trying to find the general solution of a linear system, it would be an absolute disaster. So please don't misunderstand this to go have a wider scope than it actually does. Okay, but here's where we can do column operations when we're calculating determinants. And here's why. Because transposing a matrix doesn't affect its determinant. So think about it this way. If you wanted to interchange 2 columns, you could think about it as this. Well, transpose the matrix, which has no effect on determinant, interchange the corresponding rows, because you turn all the columns into rows when you take the transpose, and interchange those rows and then transpose it back. And that's equivalent to performing a column operation. So that's how we can approach this. But we don't actually have to take the transpose every time because transposing doesn't affect determinants. But that's just a justification for why you can perform column operations when you're computing determinants. But this is what I mean by it's a very narrow scope when this is applicable. So you can perform column operations to help compute determinants, and that's the only time that we're going to allow ourselves to do that. But let's look at an example of how we might apply that. So we'll find a determinant of this 4x4 matrix. So which is given by A, big surprise, quite often is, but that's how we'll start, write determinant of A, and we'll use the same notation. We're going to take the determinant of this 4x4 matrix. Okay, so that's the 4x4 matrix, and we want to take its determinant. So you look around and you can see, well, you could start doing row operations. But this 3 and this 6 could be eliminated if we allow ourselves to do column operations because of the 1 and the 2 over here. Let's say we subtract column 1 from column 4 3 times. Well, let's write that down first, and then again I want to run through exactly why we're allowed to do that in just a moment. But let me write it down first. So we're going to take column 4. So we're using C now instead of R, right, to represent the columns. So take column 4. We're going to use the exact same notation otherwise, right? So take column 4 and replace it with column 4 minus 3 times column 1. So how can we get away with this? What is it that allows us to perform now column operations? Well, think about it this way. We're allowed to take the transpose, and that's not going to change the determinant. So if I wanted to, I could write equals, draw 2 more vertical lines, and then just fill in exactly the transpose of this matrix. Then I could take row 1 and replace it with row 1, I could take row 4 and replace it with row 4 minus 3 row 1, which doesn't have any effect on determinants. And then I could take the transpose again and transpose the matrix back. And that would be exactly equivalent to performing this column operation. So really, you can think of it as you're really doing row operations, but you're just sandwiching them with transposes. Okay, so that's why we're allowed to do this. Okay, and ask yourself, what effect would it have if we did the corresponding row operation? So that is, if we were to take row 4 and replace it with row 4 minus 3 row 1, well, that would have 0 effect on the determinant because adding or subtracting a multiple of one row to another does not change the determinant. And since neither does transposing, this column operation is going to have the same effect, which is nothing. So we get to just perform that operation for free, and we don't have to account for any change to the determinant because there is none. Okay, so let's do this row operation, the column operation. I misspoke. So the first 3 columns are not going to change. So let's fill those in. 0, 7, 6, 3, and then our third column, 0, 0, 3, 1. So that won't change. But then in the fourth column, 3 minus 3 times 1 will be 0. 6 minus 3 times 2 will be 6 minus 6. 0 minus 3 times 0 is 0, and then negative 5 minus 3 times 7, that's negative 5 minus 21, so that's negative 26. Okay, so that's what we get. And hey, now it's a lower triangular matrix. That worked out excellent, because now, remember, the determinant of a triangular matrix is just the product of the entries along the main diagonal. So that's going to work out quite nicely. So our determinant, we're essentially done. It's just a little bit of arithmetic now. 1 times 7 times 3 times negative 26. And those are certainly big enough numbers that it's annoying to do it by hand, and it's a bit much to do in your head, so don't feel bad about grabbing a calculator. And if you go ahead and grab a calculator, what you'll find is that you get a negative 546. So that is an example of finding a determinant using column operations. But please don't misunderstand. It's not like I've been just secretly withholding column operations from you all this time, and that it's really something that you can do whenever you want. That is not the case. If you do this without care and you start doing column operations where they're not appropriate, you can run into trouble. So just remember this. You're allowed to do column operations if you are computing determinants. For now, that's the only time you'll be allowed to do that.